This is the last video about solubility in Unit 3. In this video, I'll just be introducing some final things you should know about solutions before we revisit them in Unit 8. First off, we already know the rule like dissolves like. That's super important. Make sure you're familiar with it. When we say this, we are stating that molecules with similar intermolecular forces will dissolve in one another. Polar solvents will dissolve polar solutes, and nonpolar solvents will dissolve nonpolar solutes. However, what is actually happening when something is being dissolved? And how come only likes can dissolve likes? Remember that the reason molecules form both intermolecular and intramolecular attractions with one another is to lower their overall energy and be more stable. This is a ground law in chemistry, and it's the rule that molecules follow. It's not like they're doing all this bonding stuff out of choice. Just like the purpose of a species is to reproduce, the purpose of a molecule is to lower its energy as much as it can. And so if we lower the energy by forming strong attractions, then the formation of strong attractions is favored. Let's shelve that thought for a short minute. What happens when I add a solvent to a solute? What does it actually look like when something dissolves? Remember back to the example of water dissolving an ionic salt. The solvent molecules of water attract to the solute molecules, our salt, and the new intermolecular forces they are forming, which we see exhibited here, are stronger than the original forces holding the solute together. Therefore, the solute dissolves in the solvent and a solution is formed. And so we can see that, right? Our positive cation in our original salt forms lots of strong intermolecular attractions with the water molecules. The same goes for our anion, that's going to form strong intermolecular attractions with the water molecules, and these intermolecular attractions with the water molecules are stronger than the ones holding the salt together. It's going to break into its individual ions. Effectively, it is dissolved. Water is polar, meaning that it wants to form strong intermolecular forces with other molecules, because it has very polarizable dipoles. If we introduce another very polar solute into water, such as ethanol, it will readily dissolve. Because again, they are able to form new and very strong intermolecular attractions with one another, which overcome the original forces holding the solute together. So again, just to summarize, because both of these molecules are polar, they are both physically capable of forming strong intermolecular forces with each other, and so they will form these forces, and the formation of these intermolecular forces between water and ethanol molecules is what it means for something to actually be dissolved. For something to be dissolved, it means we are forming intermolecular forces between our particles. However, what if we were now to introduce water, which again is a polar solvent, into a non-polar solute, such as olive oil? The intermolecular forces holding water molecules with one another are much stronger than any force of attraction they could form with an oil molecule. Because olive oil is non-polar, so there's like London dispersion forces holding together. There's nothing else. There are no strong IMFs in olive oil. And so can water form strong IMFs with olive oil? No, they're going to be relatively weak. This is just the nature of IMFs. And so would the water rather form strong hydrogen bonds with other water molecules or weak bonds with the oil molecules? Of course, they're going to want to form stronger hydrogen bonds with other water molecules. There is no reason nor force of attraction that is driving water molecules to form IMFs with oil molecules. And so the solutions will not dissolve into one another, they will not mix. And so that's something you absolutely have to understand, because that right there is the reason why we say that likes dissolve like. Because molecules with a similar polarity are able to form preferential intermolecular forces with one another. Polar molecules can form strong IMFs with other polar molecules, so they mix. But if you're not going to be forming strong IMFs with nonpolar molecules, then just form the IMFs with yourself. And that's why they don't mix. This also explains why nonpolar molecules still dissolve nonpolar molecules. Both the intermolecular forces holding olive oil and paint thinner molecules to one another are quite weak. So why can't these molecules just mix with one another? If olive oil molecules are forming weak intermolecular forces with other olive oil molecules, well then forming weak intermolecular forces with paint thinner molecules isn't going to drastically raise their energy, and so it's still preferential. That's why nonpolar mixes with nonpolar. I hope that made sense, because it's crucial that you have a strong understanding of this principle defining the actual reason of solubility. And so now that we have a strong knowledge over this process, how will changes in the properties of our molecules affect solubility. If we increase the temperature of our components, then their solubility will also increase, most of the time. There's like a handful of molecules that are going to reject this trend, but on the average, it holds true. The very, very, very large average. So don't worry about those outliers. This is mainly due to the fact that our molecules will be moving quicker at a higher temperature, so the dissolution process will happen quicker. They are more soluble. And then obviously, as we increase the similar strength of the intermolecular forces of our molecules, our solubility will also increase. And again, this is everything we just talked about. If they can form stronger IMFs between one another, they will be more soluble. William Henry was an English chemist during the 1700s, and he came up with the law known as Henry's law. His law states the solubility of a gas is directly proportional to the pressure of that gas above the liquid. As we increase the pressure that the gas exerts above the liquid, so does the solubility of the gas. That also increases. Another thing you need to know about the solubility of gases is that as we increase temperature, their solubility actually decreases. This is opposite from the other substances we just talked about. It's also explained using Le Chatelier's principles, which you're going to be learning about in Unit 7. So don't worry about the exact explanation for that just yet. Now that we know exactly why solutions form, there are 3 different types we should be familiar with. Unsaturated solutions are ones in which more solute can be dissolved. Saturated solutions already contain the maximum amount of solute. We cannot dissolve any more solute in a saturated solution. And supersaturated solutions contain more solute than normally possible. Additional solute would not get dissolved, it would just precipitate out of the solution. So those are the 3 classifications for a solution. Just be aware of that terminology. And for the last part of this video, let's now look at something called a solubility graph. These graphs show how much of a solute we can dissolve in a solvent and at what temperature. For example, this graph has 8 different substances labeled on it. Our x-axis is the temperature in Celsius of our solution, and the y-axis represents how many grams of our solute we can dissolve per 100 grams of water. And an important thing to notice about these graphs is our trend with temperature. As the temperature increases, we can dissolve more of something in our solvent. For instance, at 20 degrees Celsius, we can only dissolve around 27 grams of potassium nitrate. But at 80 degrees centigrade, this value will increase greatly, and we can dissolve something more like 155 grams of potassium nitrate. And so it's important that you realize that these graphs show that rule in action. Something that'll be expected of you in AP Chemistry is to use one of these solubility graphs to tell whether a solution is unsaturated, saturated, or supersaturated. To do this, find the amount of your substance that's dissolved and at what temperature, and compare that point to the line of solubility. For instance, if we have 180 grams of sugar dissolved at 40 degrees Celsius in 100 grams of water, our point would be right here. This is an unsaturated solution. If the point is below the line, it's unsaturated. What about if we now raise this to 300 grams of sugar dissolved in 100 grams of water at 40 degrees Celsius? That's the point right here. That is a supersaturated solution. And then lastly, what if at 0 degrees Celsius, we have 180 grams of sugar dissolved in 100 grams of water? That's the point right here. That is on the line, and so we say that solution is saturated. And with that being said, that's everything you need to know about solubility for your chemistry class. If any of this was unclear, I recommend rewatching parts of the video. If it's still not making sense, take a break and come back after. Thank you for watching.